between the two numbers. This is anything between 0 and 1. Well, we didn't have any. Anything between 1 and 2, we didn't have any. Anything between 2 and 3, we didn't have any. Between 3 and 4, we had 16. So the tally mark at 3 and the tally mark at 4, we're going to put the bar between them and go all the way up to 16. That shows us that between 3 and 4 there was a frequency of 16, and this is the rates of return. Between 4 and 5 we had 13. So we'll go halfway between 12 and 14. And the bars are touching again, it's a continuous set. Then between 5 and 6 we had 4. Between 6 and 7 we had 1. Between 7 and 8 we had none, so make sure to make that blank spot. Then 8 and 9 we had 1. 9 and 10, none, so blank spot. Between 10 and 11 we had 2. Between 11 and 12 we had 2. And between 12 and 13 we had 1. So all those blank spots are super important. We got to make sure we show where there's gaps. So this clearly shows us the data and how it has the pattern it's had over 5 years. So it's a continuous histogram. The only difference is how you draw your numbers. Everything else is about the same. All right. The next type of plot is something you might not have heard of before. It's called a stem and leaf plot. It's one that I like to use. It's quick and easy. So here are the textbook directions for how to make a stem and leaf. So it says the stem of the data value will consist of the digits, this always sounds weird, to the left of the rightmost digit. Anything to the left of the very last digit will be a stem. The leaf will always be the rightmost digit, or the last digit. The last digit is the leaf. Everything before the last digit is a stem. We're going to write the stems in a vertical column in increasing order, and draw a vertical line to the right of the stems, and we'll go through these with an example. Step 3, we're going to write each leaf corresponding to the stems to the right of that vertical line. Now step 4, within each stem, rearrange the leaves in ascending order, and then you title it and include a legend. I don't worry about step 4 if you're creating one by hand. On your homework, you'll have to rearrange in ascending order, but we're going to make a couple by hand, and that's just, I'll show you what it means, but it's just rewriting the whole thing again, which I don't think is necessary when you're working by hand. All right, so let's see how this works. So we have this example from the book. It's different grams of fat in a McDonald's breakfast. So the following data represent the number of grams of fat in breakfast meals offered at McDonald's. So here's a sample of different breakfast meals, different grams of fat. We need to find the lowest value, which looks like 3, and the highest value, 50-something, 59. Looks like 59 is the highest. So the lowest and the highest. Because most of these have 2 digits, we're going to turn 3 into 03, and we're going to turn 9 into 09, similar to how we did with the random digit table. If these all have 2 digits, we're just going to tack on 2 digits for any single digit value. Now, the way this works is the rightmost digit is the leaf, and anything to the left, no matter how many digits you have, anything to the left is the stem. In this situation, we have 1 digit for the stem and 1 digit for the leaf. The leaf will always have 1 digit. The stem can have as many digits to the left as it needs. So in our situation, we have 0, 1, 2, all the way through 5 as our stem. So we're going to do 0, 1, 2, 3, 4, 5. Let me use a darker color. 0, 1, 2, 3, 4, 5. And you just keep going. Again, you don't skip any digits here from lowest to highest. Even if one's missing, we just listed anyway. Then we draw a bar to the right of those digits. And it might help to put kind of a dotted line between, when we're doing this by hand, just to line everything up. Just a gentle dotted line just to kind of help us see what we're looking at. So then we start looking at the data and recording what we see. So the first number I see is 12. The stem part is 1, and then I'm going to put a 2 next to it, and that represents 12. Then I'm going to come over here to 22. The first 2 is the stem, the second 2 is the leaf. So I find 2 on the stem and put a 2 for the leaf. Then I see 27, so it's the same stem of 2 and then a 7. Then I see 0, 3, so I'm going to go to 0 and write 3. Then I see 25, back to 2, and I'll put a 5. So this is 22, 27, 25. Then we have 30, so I'm going to go to 3 and put a 0. 32, go to 3, put a 2. 37, go to 3, put a 7. 27, go to 2, put a 7. So we have two 27s. So 27, 25, 27. And then 31, so I put a 1. 11, so I go to the 1 and put a 1. So this is 1, 2, and 1, 1. 16, so I put a 6 on the 1 stem. 21, 32, 22, 46, 51, 55, 59, 16, 36, 39, just 0, 9, and then 24. So each leaf represents one of the data points, and we read it stem, leaf. So 0, 3, and then stem, leaf again. So we keep going back to the stem, stem, leaf, stem, leaf. So the stem of 0 has 2 leaves. The stem of 1 has 4 different datas, 1, 2, 1, 1, 1, 6, and 1, 6. So this tells us all the data, kind of lowest to highest, sorting by the stems. And again, we'll be able to kind of smooth over to see where the majority of the data fall. The book is going to have you rewrite once you've made it. So you'll make your stem again, and you'll put the leaves in order. Well, the 3 and the 9 are already in order. 2, 1, 6, 6. I'm going to put the 1 first, and then the 2, and then the 6s. Here I'm going to put the 1 first, and then there's 2 2s. There's a 4, a 5, and 2 7s. So I'm rearranging just the leaves, least to greatest, least at the stem, and then greatest at the edge. And then I'm going to arrange these. I have 2 0s, a 1, 2 2s, a 6, and a 7, and then a 6, and 1, 5, 9 are already in order. So it's going to make the same shape. We're just rearranging the leaves from least to greatest. This helps us find our minimum value, and it helps us find our maximum value, our lowest and our highest, if you arrange them from least to greatest. So that's how the computer's going to ask you to do it. Back-to-back stem and leaves are really useful in comparing data, so we'll make one of those next. I'm not going to rearrange the leaves on this one, we're just going to make it once. So we have actors and actresses, and you can pick one side or the other. We're going to have a stem in the middle, and then we can have actor on one side and actress on the other. Doesn't matter which is which. We just need to find the lowest age for actors, which looks like 20-something, 29 maybe. Unless I'm missing one, 29. And then the youngest age for actress, there's 21. Anything less than 21. So we need to find the lowest, which would be a stem of 2. And then we need to find the highest. I see 60. Oh, I see 76. Anything in the 80s? And then again, scan actresses. I don't think there's, oh, nope, there's an 80. So we have to count all the way to 8. 5, 6, 7, 8. And then you do one at a time. The actors will kind of go backwards. Your leaves will go to the left, and then actress, your leaves will go to the right. So I'm just going to take a minute and draw this out, and you can follow along or do it yourself. We're not going to rearrange this time. We're just going to go with what we have. And I'll show you how to compare. I did not give myself enough room, but we'll get the idea. So when you do your actors to the left, it becomes very clear that 30s and 40s are where the majority of your data lie. And you can see your lowest and your highest very quickly, but you can definitely see your majority of the data is in the 30s and 40s. When we do the actress, it'll be the same idea. So I'm going to run through this. You can do so on your own. You can go in any order. I always go across and then down, but it doesn't really matter. Just don't skip one and don't count one twice. So whichever order makes sense to you so you don't mess up your counting. I don't know if you can see that on the dark. That might help. Turn the light on. That might help it. Oh, where was I? 33, 36. You just keep going in whatever order you're going in. 35, 35, 28. Ooh, I ran out of room. 30. 29 and 61. So the actresses, it makes it clear that their age is on average younger. You can kind of see the majority of theirs are younger, but then they also had the maximum of 80. So you can compare two sets of data. You don't have to tally anything. You don't have to get relative frequencies. You don't have to make a histogram. The stem and leaf is just quick and easy. You don't have to count anything. You just make it, and you can easily compare sets of data. So it's kind of tedious to make, but I think it's a good summary of what you're looking at without doing much in the way of calculations. We also have dot plots, which we're not going to spend too much time on dot plots, but if we take that same set of data from Wendy's, how many people arrived in those 15-minute intervals, we can, instead of tallying and counting and getting relative frequencies, we can take dots, and when we see a 7, we'll put a dot at 7. When we see a 6, we'll put a dot at 6. 6 again, 6 again, 4. It's kind of a way of tallying your different results, but we put them in stacked dots. So anytime we have a repeat, we put another dot above it. 5, 6 again, 6 again, 11. And we just keep putting dots at every value. And it kind of gives us our histogram roughly. So it's a quick way to roughly get a histogram of our data. So without being too fancy, just kind of gives us that rough visual of what we're looking at, and that's called a dot plot. There's also time series plots, which we don't really focus on too much. Anytime the data is being measured over time, so this x-axis is time, anytime, year, minute, whatever, anytime the time is being measured on the x-axis, instead of making a bunch of bars, we just put a dot at the different values. and then connect those dots to find the pattern over time. So we're looking over time. They do this with housing, they do this with gas prices. The stock market always follows by month or hour or minute different time intervals. So anytime you're listing by a measure of time, you make what's called a time series plot. From all of these different plots, usually we use histograms. We can technically use this from dot plots or stem and leaf, but we generally use histograms. There are 4 shapes that our distributions can have. The first shape is called uniform. And it's kind of like all the soldiers lined up in uniform. They're all the same frequency. So if I had these values 0 through 20 and tallied them up and they all came out with the same frequency, that would make a uniform distribution. And then we have the most common, which we're going to call bell-shaped, where you have a few and then you have the majority and then you have a few. So you have a few low, a few high, and the majority in the middle. And this is the most common type of shape, is bell-shaped. It will not be exactly symmetrical, but it will be roughly symmetrical. Uniform distributions are also technically symmetrical. Remember, symmetrical means you can cut it in half and fold it over itself, and it makes the same on each side. So it's roughly a mirror image along the center. Then we have 2 types of distributions that are kind of weird. The first one is called skewed to the right. Sometimes you'll see it called skewed positive, and that's when the majority of your data are low, but you have a few extreme values. So you have a few extreme high values. So you have this one value, and it's making your histogram kind of pull to the right. Majority of your data is low, you have an extremely high value to the right. So it's not symmetrical, it's skewed, it's off-centered. Similarly, you have skewed to the left, which is sometimes called skewed negative. That's when the majority of your data are generally higher and you have a few extreme lows, and those extreme lows are pulling your tail. So extreme lows. So the part of the curve that kind of tapers off, that is called a tail. So if I use that phrase, it's the part that tapers off, and that is our tail. So the tail goes to the right for skewed right, and the tail goes to the left for skewed left. These are the shapes we'll be using throughout the course. Uniform we'll mention a little bit in Chapter 7, but we don't deal with that much. Bell-shaped is what most of our data is all about bell-shaped. In Chapter 3 and then on in the other chapters. Skewed distributions, we don't spend much time on skewed distributions because they're analyzed in a very different way. So we focus our energy on bell-shaped distributions. Those are the 4 shapes, and you can find those shapes from histograms, from stem and leaf plots, from dot plots, and you can kind of see the shape the data are taking. The last bit of Chapter 2 is really short. The last section is about graphical misrepresentations of data. So this is when we're misrepresenting our data, which happens all the time. The quote in the book says that the statistics is the only science that enables different experts using the same, I don't know if you can see that, the same figures to draw different conclusions. So we're looking at the same set of data and they draw different conclusions. One book I have is called How to Lie with Statistics. And I don't know if you can see the image. It's a little guy sweeping numbers under the carpet. So it's really how to manipulate the numbers to make them say what you want them to say. And we see this all the time in commercials. We see this in political campaigns, all kinds of different ways to manipulate the numbers to make them work in your favor. Another quote that I like is, statisticians, no one knows what we're doing, so we're always right. People just assume that percentages are correct when they hear them. We see them on Facebook, we see them on the news, we hear them on the radio, and we just assume that they're correct. We don't give them a second thought. And I think after this course, you'll kind of start slowing down and considering where those numbers came from, what do they really mean, and are they actually accurate. So Hopefully this course will open your eyes a little bit so that you're not misled with all of these percentages that we always hear about. So just a couple examples of how this can happen. I just pulled a couple out of the book. So in this situation, it's a security company, and it's a summer ad campaign. So they're trying to sell their security program. And they say, when you leave for vacation, burglars leave for work. And they say, according to the FBI, roughly 18% of home burglaries in 2009 occurred during the peak vacation months of July and August. And they give this nice little graph in their advertisement. And it wants you to think about what is wrong with this graphic. And there's a couple things going on here. If we just look at the bars and we don't look at the numbers, then it makes it look like July and August are twice as much as the other months. The first thing I noticed is that other months represent the whole rest of the calendar, and July and August are just two of the months. Another thing that I noticed is that 8.2 and 18 don't add to 100. So the first question is, where are those numbers coming from? They don't add to 100%. If this represents the entire calendar year, these should represent 100% of the information. So it kind of discusses about that. And it tells us that the average percent for the months of July and August have been combined. And the other months have been averaged. An average for each month versus a combined average. Which happens all the time because, again, people just trust the numbers and they don't look behind where those numbers came from. They don't look at the raw data to see really what's going on. So this ad campaign, this is an average per month, and this is a combined value. We would have never known that if we wouldn't have dug a little bit deeper into where those numbers are coming from. So they redrew the graphic where it lists all of the months, January through December, and it lists the percentages of each individual month. And here, this looks more uniform. Not exactly uniform, but more uniform. You might notice that February is lower. Well, February only has 28 days, so that might be why the percentage is slightly lower. But you can see that they all hover right around 8%. Now, July and August are slightly higher than the others. They both have 31 days, so that's one thing to consider. And maybe they are slightly higher in the summer with all the students out of school. However, they're not drastically twice as much as the rest of the months. So this figure is a more accurate representation of really what we're looking at. Here's another one. Let's kind of glance over that. We have different political parties and their opinion regarding a certain court case. If you just look at the bars and you don't look at the numbers, it looks like Democrats are much more agreed than the others. However, if you look at the scale here, they did not start at 0. Typically we start at 0, and they started at 53. They kind of zoomed in on just those values. And if you look at the second figure, it actually starts at 0, and it doesn't look quite as ridiculous. All they did in the other picture is zoom in right there. When you zoom in too much, it's going to look very different. So it's important to have your scales drawn properly, and you always want to double check scales on different figures that you're looking at online or in magazines. You always want to check those scales to really see what you're looking at. Here's another one. We have average SAT math scores over time. And so we notice here that we're looking at different years. And these bars kind of go like this. And these bars kind of look flat, even though it's the same set of data. We look at the scales again, 495 to 520, so they kind of zoomed way in. Here they zoomed out to 200. And maybe it is appropriate to zoom in, but here is an actual correct display of the SAT math scores over time. Again, if we're going over time, we want to look at a time plot. And it's okay to zoom in, but we use this little zigzag to help us realize that we've zoomed in. So that tells us that we've skipped values. We're not starting at 0. So that little lightning bolt zigzag tells us that we're not starting at 0. And a time series plot is more appropriate when we're plotting things over time. And that shows you how the scores have changed. So that's just another way of displaying data properly. For your concerns, you just need to be able to recognize the difference and maybe spot a misrepresentation that you notice. All right, so that is chapter 2. We've discussed frequency distributions. We know what a relative frequency is. We know how to display categorical data with bar charts. We know how to make a histogram for discrete and continuous, stem and leaf, dot plots and time series plots, and we've discussed misrepresentations of data. So that is chapter 2.